This last video is going to be on integration using substitutions. Now, if you have a simple integral, the integral of f of x dx, and you happen to know its antiderivative f of x such that f prime of x is equal to f of x, then you can simply write down the integral of f of x dx is equal to capital F of x plus a constant. For instance, if you had the simple integral of cosine of x dx, you know its antiderivative is sine of x, so the integral would be sine of x plus an arbitrary constant. However, suppose you had a more complicated expression, the integral of f of g of x, and you had inside the integral g prime of x. So this is a little more complicated expression, but we can look at it, and if we see another integral that follows the same kind of pattern, it turns out that we can integrate this using a substitution. So suppose we let u equal g of x. Notice that du dx is just simply g prime of x, and looking at the differential, we get du is equal to g prime of x dx. Then we can see that portion I'm going to encircle here, g prime of x dx, could be replaced by du. And we already know that u is equal to g of x, so that this integral is equal to, doing the substitution, f of u du. And if we know the antiderivative of f to be capital F of u, then the integral is capital F of u plus an arbitrary constant. And then we can go back and substitute in u equal g of x. And so the answer is f of g of x plus a constant. So if we see an integral that has that kind of form or pattern, we can, number one, choose some u equal g of x, calculate du equal g prime of x dx, and then substitute g prime of x dx equal to du, and u equal g of x, and then perform the integration, which should be a lot simpler. And then finally substitute u equal g of x. So let's do several examples. The first one is going to be the integral of cosine of 5x dx. Now you could probably guess the antiderivative of cosine of 5x without using a substitution, because all you have to do is sort of figure out what it's going to be and make sure after you take the derivative that it equals cosine of 5x. But let's just pretend for a moment we didn't know that, and we let u equal 5x. So if we let u equal 5x, du dx equals 5, and we get du is equal to 5 dx. So dx is equal to du over 5. And of course, the 5x is used, so that integral is equal to cosine of u du divided by 5. And we know that that is equal to sine of u over 5 plus an arbitrary constant. So we get sine of 5x after we resubstitute for u plus a constant. Another example is, suppose we had x times x squared plus 1 to the 4th power dx. Notice that if we let u equals x squared plus 1, du dx is equal to 2x. So du is equal to 2x dx, and x dx is equal to du over 2. So this portion gets to be du over 2. And we already have made the substitution, so the integral becomes u to the 4th divided by 2 du, which is u to the 5th over 10 using the power rule plus a constant, and then resubstituting what u is, we get that the integral is x squared plus 1 to the 5th power divided by 10 plus a constant. Another example, suppose we had the integral of x squared, suppose we had the integral of x times the square root of x squared plus 1 dx, and we let u equal x squared plus 1, and we get du is equal to 2x dx, and so xd this should be dx, by the way. Then we get that x dx is equal to du over 2. So this will become du over 2 in the substitution. And so the integral becomes the integral of u to the 1/2, taking into account the square root, over 2 du, which can be integrated as u to the 3/2 divided by 2 times 3/2 plus a constant. So the answer is u to the 3/2 over 3 plus a constant. Resubstituting, we get x squared plus 1 to the 3/2 divided by 3 plus a constant. Another example, suppose you had the integral of secant squared of x times tangent of x plus 3 dx. Notice that the derivative of tangent is equal to secant squared, and if we let u equal tangent of x plus 3, we will get du dx is equal to secant squared of x, and so secant squared of x dx would equal to du. So this portion becomes du, and the full substitution gives us the integral of u du is equal to u squared over 2 plus an arbitrary constant, and we get, after resubstituting for u equal tangent of x plus 3, tangent of x plus 3 squared over 2 plus a constant. And then finally, last example, the integral of 1 over x squared e to the 1 over x dx. Notice that if you let u equal 1 over x, that du is equal to minus 1 over x squared dx. So 1 over x squared dx is equal to minus du. That means that this portion gets to be minus du, so the whole integral becomes the integral, or minus the integral, of e to the u du. The integral of e to the u is just e to the u, so we have minus e to the u plus a constant. And because u is equal to 1 over x, we get that the answer is minus e to the 1 over x plus a constant.